And let me start with a scenario. Just imagine on one fine day you wake up from your sleep and realize that all your security measures, including social media, including your bank accounts, or including anything connected to the world, is compromised. How bad that would be. On a fine day, you understand that whatever you are thinking, like it's all secured, is now compromised. Maybe you will wonder, like, okay, it's just an imagination, and if I stop the imagination, it's all done, right? But what if I tell you that there is a slight possibility for this threat to happen in the near future? And that threat will be the one which we are focusing today. Welcome to the Post-Quantum Cryptography, and my name is Ajith, and today we will be talking about what is that threat all about, and specifically how it will be impact on the embedded Linux systems. Before going to directly to the presentation, a couple of things. One, this presentation is all expressed views from my side. It's not related to any company or so forth. And the second one, the questions I'll be taking at the end of the session because we have a lot of to cover within less time. And the third one, this is actually targeting for the beginner session, so don't expect any patch sets or any implementation, that too after a heavy lunch. So this will be a very basic stuff. And comes to the session, it's all boiled down to the famous quote, an ounce of prevention is worth a pound of cure. I mean, today's agenda all will be comes to this. This is a famous Benjamin Franklin quote. So I'll tell you why this is coming into the end. Now, when I talk to the Linux and embedded Linux specifically, why Linux is so important in the security? Let us start with that. We'll see some of those Linux statistics. According to the according to Blackdown, the world's top 500 fastest computers currently running on the Linux. And that is something around 91.5% of all the supercomputers, and 96.3% of top of 1 million web servers currently running on the Linux. Similarly, there are actively 600 Linux distros, and 85% of smartphones, as you know today, all are running Android, which is running Linux on top of it. And Linux runs 92% of virtual machines in the cloud, such as AWS, Google Cloud, Azure, etc. And about 85% of the business use Linux because it's flexible and it saves a lot of money in the production environment. This is where even the embedded system nowadays using Linux predominantly. We'll come to the later stage, like why Linux and embedded system importance here. And the Linux is one of the main operating systems for the containers now. And thanks to Kubernetes, Docker, 85% of use, all are like Linux. So you may be seeing why Linux is very important when it comes to the user. Now we'll come to the embedded security. So this is not different from a standard security. All are working under CIA, confidentiality, integrity, and availability. And if you see any domain, such as IoT and automotive, industrial automation, medical, everywhere security is very crucial now. I mean, for example, if you're taking an automotive sector, the latest trend is CV2X. It's nothing but connected vehicles. Vehicle can communicate one to another. And if one car or one truck got compromised, it will lead to all the trucks to go compromised. So that important the security is now. And when it comes to the security, it should be always a confidentiality place. I mean, for example, it has to be manage the sensitive informations, and the integrity it has to keep, and it should be available always. It's not like you're switching off the system and telling my system is secure. So it should be available to the user at any point of time. And embedded system, when it particularly comes, it actually have its own challenges. For example, it usually will be run it with a constrained environments, and cryptographic algorithm usually need more enhanced accelerations. So there is a trade-off between low-performance embedded system versus high security. We will see how the security things will be come into place. So importance of security, as I said, IoT, if you see, all are connected in nowadays world. So everything you have is already connected and can have access to other person. And we have a sensitive data handling and remote accessibility. And device lifecycle is very crucial for embedded system. For example, unlike any other systems, Usually, the embedded systems is meant for longer lifespan. For example, there are some systems which we are actually making for 10 to 20 years without any change. For example, if you see a medical healthcare devices, usually it will not go for undergoing any changes frequently because once it's stable, it has to run without any issues. So their security should be future-proof. That's an important role. And regulatory compliances, there are many like GDPR, HIPPA, NIST, and ISO 27001, which require strong encryption methods and protective sensing data. Now, come to the security, we will see what and all current security measures we are having. Basically, it will be classified as symmetric, asymmetric, and hash-based. Symmetric cryptography, one example would be AES, which is widely using. So if you see here, the symmetric, nothing but the same key is actually using for both encryption as well as decryption. For example, if you have a plain text or any data, you have to take it and encrypt it using a key, which we are calling secret key. And on the other side, you have an encrypted document, which will be decrypted using the same key. So this is nothing but the AES or any symmetric algorithms follows. Now, the problem with this is like managing this key is very important because this key is actually, belongs to both sender and the receiver. And while sending or somewhere it is compromised, then it is very easy to decrypt or encrypt using any other malicious attacks. So key management is one of the important points on the symmetric cryptography, and improper key management can lead to security breaches. Now comes to the second versions, asymmetric cryptography. For example, we have RSA or elliptical curve. So here we have basically two keys instead of the previous one, which have only single key. So for example, this is a typical thing like Alice send to Bob send decrypt like that. The important point here is like the signing, whatever they do, is with the private key of the sender, and the verify, whatever we have to do, is with the public key. So in case the public key is compromised, which is okay, because the private key is always there, remain intact or secure. Both RSA and elliptical uses the same. Only thing is, people or the community prefer ECC over the RSA because it have less overhead. But it depends on the trade-off. Like, for example, if somebody required a lesser memory, somebody required more security, always they can increase the key sizes, and it can increase the security. Now comes to the third version, which is hashing algorithms. Basically, hashes nothing but if you have an input and you do some hash functions, you will get a definite bits out of it. And if you change, for example, in this case, I'm giving 000, and you do a hash function. Hash function can be anything, SHA, i.MX, or any other hash functions. You will get a unique bits. For example, SHA 256. It will give a 256 bits, no matter how the input size is. Similarly, if you change any single bit, like for example 001, you will get an entirely different hash. So this is actually very unique, and this usually use it for example, a boot time verifications. Or if you are using a password mechanism, usually password will not be stored written as a plain text in your server. It will be as a hash. So only when you are giving a proper password, then only you will get the similar hash for verification, and you will get it back the verification success. So hash is actually very useful there. Now we'll come to the current algorithms risk. Basically, all the algorithms, either it is symmetric, asymmetric, or the hash, all rely on mathematical problems. And current algorithms on a classical computers are known for years to crack or break the algorithm, so which is very safe. For example, if you are seeing all the AES or RSA or whatever it is, it's all are proven to work on the classical computers, even the supercomputers in that matter, because all are rely on the bits, zeros or ones, and that will take years to break with the classical computer. But there are two threats or the theorems which is telling this can cause a problem in the future. For example, the Shor's algorithm actually telling the public keys cryptography can break if there is a provision given by some other future. For example, classical computer, if you see, it cannot break easily. But if there is a provision for multiple computational power comes in together, then the efficiency factor of large number can reduce, and it can solve this algorithm. So this can directly impact the RSA elliptical or Diffie-Hellman kind of public key cryptographies. The other one is Grover's algorithm, which is actually not telling to break the symmetric key, but it will weaken the symmetric key. For example, it will be speed up the brute force mechanism, and it may reduce the security level of symmetric keys like AES or something. Now, the natural question will come like, see, currently all are using RSA, all are using AES, and this will take years to break the classical computer case. Then what is the risk we are actually talking about? Welcome to the quantum computers, and this is something maybe almost everybody knowing by this time. So the quantum computers are actually a different mechanism. It's not like a supercomputer as per. The way it works is entirely different from the classical computers or the supercomputers. For example, if you see here, on this side, the classical logical gates, whatever we studied in college or whatever we are using, is mainly rely on AND, NOT, or all the gates. And the quantum logic gates are entirely different. It have its own gate mechanism, which actually rely on qubits. The next slide, I will be talk more about the behavior of the quantum computers. But in short, it actually have some quantum mechanics, similarly, for example, superpositioning, entanglement, and quantum parallelism. Now we'll go to the basics of quantum computer, and since this is a beginner talk, I'll be touch upon the basics. I'll not go into the details. Now, we'll talk about the qubits. Qubits is actually a quantum bits, which actually something like Bosch sphere representation, if you see. For example, this is the center, and these are the axes. If you see, these are vectors, and just imagine, like for example, these are the possibilities one bit can accommodate. I mean, if you see the classical computers, you can only get either 0 or 1 at a time. When it comes to quantum computers, it can sustain either 0 or 1 or both at the same time. For example, if you are seeing a quantum bits, it can represent 1 and 0 at the same time, which is maybe a confusing factor when we are coming to the classical computers. But in quantum, it is possible. And for example, if you are considering a 3 bits in the classical computer, it can be have, see, for example, 8 possibilities, right? For example, 0, 0, 2, 1, 1, 1. We are actually giving 8 possibilities. And all are like different states in the classical computers. But when it comes to quantum, all can represent with 3 qubits. That's the power of quantum. And this actually provides exponential computers power. For example, if you are taking a classical computer, the way you are actually dealing with a problem, it takes, for example, n number of steps. The quantum computer actually do it within less than that n number of times. Now, the another concept we are talking about is the entanglement. Entanglement is actually nothing but the quantum linking. What actually entanglement is telling, like, for example, if you have a qubit and the other qubit, if you're changing on one qubit, it will reflect on the other one. I mean, no matter how far it is. It's a quantum physics philosophy, and maybe you can search later. But why it is important? Because we can use this in multiple ways. For example, secure quantum communication, or the quantum key distribution are some of the real-world application for that, where you don't have to worry on this philosophy. I mean, one you are changing, the other will change even if it is far away. Now, with leveraging entanglement and the superposition, actually we can make quantum parallelism, and this will solve the complex task. For example, if you have a cryptography algorithm, which is very complex in the classical world, that can be easily done by quantum parallelism. You may be now guessing, okay, quantum parallelism is the one which is actually having a threat, which is right. Now, it's have its own challenges. I mean, when I say quantum computer can break, or the RSA, or everything is at risk, it's not just happening now. I mean, this required some more efforts to make it work, but quantum computer, if you are taking, it's have its own challenges, which people are working on and fixing it now. For example, there is a hardware limitation. It's actually extremely sensitive to the external interface. For example, the noises you are taking on the PCB or the temperature fluctuations all matters to give a false qubit value. And the quantum computers requires extreme cooling maybe near absolute zero, but this is actually evolving now. There are some company which is coming with a chip or the silicons. So there actually the cooling, they somehow bifurcated. So this is actually evolving now, and maybe you can see something like a normal chip, and which can inside contain a quantum computer. Now the scalability issue. Basically, quantum computer have limited qubits now, and when we are telling practically how to break the existing algorithm, that requires millions or stable qubits. And the last one is error correction. Quantum computer suffers from the higher error rate. When I say one qubit can accommodate both 0 and 1 at the same time, basically we will not get the correct value. It requires a lot of processing and computational to see that, okay, this is the actual 1 or this is the actual 0. Otherwise, you will get a false positive value. And the researchers are developing QEC, quantum error correction techniques, to make quantum computers more reliable. All these are like the ongoing activities. So when we are taking it to summary, the quantum computers features basic unit of data is actually, compared to the classical computer where bits, zeros, and ones, it actually have a qubit, 1, 0, or both simultaneously. And the processing power, always classical computer goes with a sequential, and quantum computer have the capability to do parallel processing or with the superpositions. And the storage, information storage actually relies on the binary logic gates like AND or NOT in the classical computers, whereas quantum computer have quantum gates such as C0, Hartman, or something like that. The main important point for today is like the security risk to cryptography. So in the classical computer, secure under current cryptographic algorithm, all whatever we have talked about, like for example, RSA, elliptical curve, or etc., are proven algorithms in the classical computers. No matter whatever computer in the classical world you are using, it's very difficult to break that system. But when it comes to quantum computer, or if you are using a quantum computer to attack a classical computer algorithm, then it can break RSA, ECC, and weaken the AES also. It's not something like already we broken, but this is a possibility. Now comes the PQC. PQC stands for Post-Quantum Crypto, which is different from the quantum crypto. So we are talking about two different things. Quantum crypto is actually the cryptographic algorithms which required for quantum computers to be secure. So for example, somebody attacked the quantum computer, how we will make secure? By writing a quantum cryptos. When it comes to post-quantum crypto, this is actually meant for the attack on the classical computers from the quantum computer. For example, somebody can attack using a quantum computer, and they can weaken the classical computers algorithms such as AES or RSA, etc. So according to the NIST, which is a standard, we need encryption methods that can stave off cyber attack from both conventional computer or the classical computer. We know today it includes supercomputers also and the quantum computers of tomorrow. So quantum computers is evolving. We don't know when it will get matured, but we should have an algorithm which actually protects us from the classical computers as well as the quantum computers, which we know which we don't know when it will come as a mature state. When it comes to the embedded systems, the challenge what we have it is like, see, even if it's taking automotive or IoT, anything, everything we are connecting. We are actually seeing the future in the connected world, and even in the automotive, as I told earlier, everything is connecting. At the same time, we cannot easily update that. We are actually relying on the small computers, which rely for years. So on a large scale, if you are taking any technology on the embedded now, we should be thinking about PQC now, rather than we are thinking like when it comes, we'll see kind of manner. So for example, it can be anything. Like, for example, it's not just automotive or something. Anything you're dealing with the data, anything you're dealing with the security sensitive informations or financials, anything you're taking, just remember PQC is required and the quantum computers are evolving. Now, these are some of the list of the quantum computer, PQC algorithms which accepted by NIST. When I talk NIST, there are other organizations in the other countries which are also working on the PQC algorithms. These are some samples. So the initial three, like for example, the Kyber, the Dilithium, and Sphinx, which actually published on the FIPS NIST website. It is available. The links are here. And this is basically giving, for example, the Kyber is actually used for the key encapsulation, which uses lattice algorithms based. I'm not going into the detail of what lattice and all. Basically, it's the dots, and you have a 3D maps kind of thing. It's very difficult to solve that problem, for example, the shortest path from two lattice vectors, using either a classical computer or a post-quantum, or quantum computers. Now, when it comes to the last two, like a Falcon and HQC, these are the latest one actually added into the NIST list. Initially, when NIST published its first proposal, the initial 3 was the part of it. Now Falcon came, and HQC is something like a backup for the Kyber. So majority, if you're seeing, all are like lattice-based, and there are some particular usage for everything. For example, there is a key encapsulation, digital signature. It depends on your need. For example, if you need a digital signature verification and you are using RSA, you can go with the dilithium in future, so that it will be actually safer, even in the quantum computer world. We'll take an example now. This is actually, I took it from the NXP website. Any board, if you take, I personally worked on NXP, so I am comfortable to take NXP as a board. So NXP boards have something called secure boot, which basically allow only the authenticated image to boot. Otherwise, it will be stop booting. So it's something like every board will be have it nowadays, even if it is TI or any other boards. So basically, what it means, like whenever you are actually having a software image, you are basically taking a hash of that image, and you are signing that with a private key. And here we are using RSA. And the final image will have both software image plus the signature. And that signature contains the hash of this one, plus the private keys will be remain on the secure boot. And before this, for example, before this process, usually the user will be already generated a private key and public key combination in the first place. So how this works is like the private key we are actually using for signing the RSA along with the hash on the secure environment, probably not your build system, maybe something like a KMS kind of servers. And the public keys are fused inside the board or the hardware. When it comes to the device booting stage, this image actually take a runtime hash. For example, the image taken, and it will be generate a runtime hash. And using the public key, it will be actually verify this one, and it will be actually decrypt and take another hash. So you have both hash. One is runtime hash, and another hash which we got it from here. Now we will verify both are same or not. So once it is same, then it is actually confirmed that whatever image is authenticated is only running here. Otherwise, what will happen, like you will get 2 different hashes if in case it is attacked or hacked by somebody else. So if it is comparing and getting the same image, then it will be allowed to boot. Otherwise, it will not do. It will ask for another person or another image to load. So this is how the normal secure boot works. And this is an easy example. But the threat here is like, currently everything is okay. But in future, if somebody can attack this device with a quantum computer, then the technology what we are using is RSA, which actually, as per Shor's algorithm, can break with the quantum computer. We don't know when, but there is a slight possibility. So how to prevent this kind of attack? The proposal or the example use case, this is not something which is already there. This is just like a proposal. We can use something called dilithium. As I told from here, the Crystals-Dilithium or MLDSA is famous for digital signatures. And in this case, we are doing nothing but digital signature verification. So instead of RSA, we can actually use something called Crystals-Dilithium. It's actually a post-quantum digital signature algorithm, and it is approved by NIST. And this is actually based on lattice, short integer solution SIS problem based, which is actually very difficult for both classical and the quantum computer to attack or solve. So what it provides a digital signature mechanism which actually safer when it comes to normal computers as well as the post-quantum or quantum computers. And it is efficient in the performance. This is actually debatable, but considering the 3 algorithms, what NIST agreed, out of that, dilithium actually provides a better performance in the embedded side kind of world. And benefits, it's actually already quantum-safe signatures and low computational powers and long-term security. So once, if you are starting a project newly, or if you are part of any security development in embedded system, keep in mind that you had to use post-PQC kind of algorithms from today rather than waiting for tomorrow, thinking that, okay, somebody else will do it. Because we don't know when it will get matured. Like, for example, on a fine day, we see ChatGPT comes and everything changed, right? Till that time, we were not even thinking that, okay, something like that can happen. So one fine day, one company will come and tell that, yeah, we have a quantum computer which can break RSA. Then what to do? We cannot change the embedded system so easily. So keep in mind that this is required now. You have to act now. And this is the actual use case. I mean, the same whatever I told. Wherever RSA comes, basically we will be taken a dilithium public private key pair, and we will be saying the firmware, I mean, any image in that matter, we will be using the firmware with a private key, and you will get a signature. That signature you will be taken into this. And the verification side, you will be actually use a public key. And this is the same method which I told earlier. So this will be actually verify, and this will be do the authentication comparison, and it will be verified based on that. So here, one more thing is like the hashes, you can also change. I mean, here, for example, SHA-256, if you are using, you can change into Sphinx or any other matter. For example, XMSS is one of the options, which is not part of the NIST, but it is actually, XMSS is also approved by NIST. Basically, it is using Merkle's root. I'm not sure how many of you know. If you know blockchain, actually it is using Merkle's root. The same algorithm is using in the XMSS, which is proven to be quantum resistant in the hash. So like that, we can take any algorithm based on our need. The final thoughts, the quantum computing is rapidly evolving, and current cryptographic systems are at risk. We have to accept that. And we have to use something like PQC algorithms such as Kyber or Dilithium or Sphinx or any whatever approved by any organization which is validated. And the transition to PQC should be start now. I mean, that's the main point here. That's where I started with that quote. For example, it's a prevention is always better than like something happened and we are changing it, actually loses billions of dollars. So we can start anything new with the PQC in mind. And how to be part of it? Actually, Linux Foundation already have a PQCA. It's called Post-Quantum Cryptography Alliance group. You can be part of it and get to know what and all happening around the community, which actually have multiple, like for example, Power and x86 ARM support. So you can make use of it. Otherwise, you can use the libraries, for example, OpenSSL 3.5 or later, actually using post-quantum cryptos. So instead of using the older one, you can start with 3.5 OpenSSL or something like that, and make use of PQC algorithm in your today's world. With that, I'm ending now, and any questions? Yeah, Mike.
Okay, so there are attacks like on the PQC that harvest now and then decrypt later. So basically, if you consider at this time also, all your data that is not encrypted, that is not basically not using PQC is already broken. So all our communication that we are doing now is not as important as the communication in defense kind of things. But
yeah, I mean, there is a slight change. For example, not all your communications, all your security is broken now. Actually, those are the theories, and that is actually can happen in the future. So currently, if you're seeing even your bank account is basically on the AES with the higher keys. So whenever somebody have a processing power, usually they will take a higher keys. Like for example, even if you're taking SHA or the SHA algorithms, it have a 512 also. So somebody who has to trade off with they have to use a 4K key or 6K key or whatever it is. Currently, it is not attacked, but when the quantum computer matures, then it will attack.
Yeah, so to establish that communication, first you have to use the asymmetric keys. That is RSA.
Okay.
That is already proved broken. So what you have to do is just take that data, harvest it, keep it in your cloud somewhere, and then 10 years down when you have actual quantum computers, you just have to run through it the entire quantum computers and you can decrypt that data at that time. So that is why the quantum computer, the PQC algorithms are needed at this time
Yes.
already. So
Yes. I mean, my all talk is actually the same, act now than later.
Yeah, okay, same thing.
I had a doubt regarding, let's assume if the hash generator or like the PQC key generator or something is written in code, right? It's not etched into silicon right now, like for the hardware devices of today.
Yeah, okay.
So what about like if the code just was changed to like, to just circumvent the whole secure process. So until and unless there is like etched silicon with the hashing function, you can't secure anything, right?
No, basically, it's all related to how mathematically good that problem is. Like, even if it is inside the silicon, we are doing nothing but the mathematical problem solving, right? For example, for example, in NXP and all, we have some crypto acceleration module called CAMP, which is actually do a hardware level of the same thing what you are doing in the software, but it will be faster and secure. But how relay that mathematical problem is important. For example, these people actually, if you see all the list, most of them are lattice-based, which is proven in the classical and the quantum. I mean, even if you are using from the software side, for example, OpenSSL 3.5 onwards, even if you get it and you try to solve the lattice problem with the shortest path, it is years to take to crack it. That's the confidence they have it. I mean, whether it is in the hardware or in the software. So it depends on the mathematical problem, which we have to take it correctly, so that both classical and the quantum computer cannot attack it easily. So that's a principle, we cannot consider like if it is coming into the hardware, then only it is secured. Because we have a lot of software applications which rely on this same cryptos, right?
I mean, just taking the consideration of booting a device,
Yeah.
there needs to be like the trust, right? The first thing that I can trust.
Okay, you're talking about the secure boot. Yeah, secure boot actually, what I told in this also, it's like we have to fuse that public key into the device.
Okay, using an OTP or something like that.
Yeah, it depends. Like, for example, I know NXP where we are using OTP fuses. So it's like a one-time programmable fuses, as per se. Once you fuse it, nobody can change it. And you can mask also that value. So similar kind of hardware mechanism should be there. That is right. And secure boot is actually for validating the hardware to boot with the authenticated image, right? So anyway, that is required in the hardware itself to authenticate. That same principle, like for example, whatever RSA doing today, has to do it with the dilithium tomorrow. Only thing is we are changing that algorithm to a more secure one. But the principle remains same.
Okay, thank you.
I hope that you got it, right? Yeah, thank you.
Hello.
Yeah.
I'm audible, right?
Yes.
I don't have a doubt over this PQC, but earlier when you were like teaching about the quantum thing,
Okay.
so initially you said like a qubit can exist between 0 and 1, and then you showed the block sphere, but then my confusion is given a vector on the block sphere, there can be infinite number of points on the block sphere itself. So
Yes.
rather than telling it to be parallelizable, I can in a way tell it to be a single qubit can be like infinitely parallelizable in a way.
You're talking about this block sphere?
Yeah, this
yeah,
one.
yeah.
So for any point on the sphere, there can be like infinite points on the sphere. So a single qubit can, in a way, express all the numbers between 0 and 1.
No, this is actually based on the vectors where you are directing. For example, if you are going into this direction, it can go both 1 or 0. In this direction, it can again say 1 or 0. And this is also can give 1 or 0. That's a directional inputs, not like infinite possibilities over here. So this is the starting point. From there, where you are directing your atoms or the superpositional ions, that can accommodate 2 values at the same time. So that is called qubits superpositioning. I mean, maybe we have to check it in detail. I mean, here it will take another some time to explain that.
No, because how I can see it, like you
Yeah.
have 3, it's a 3D sphere, right?
Yeah, it's a
So
3D
anything,
sphere.
any vector that you can make out of it, that lies on the surface of the sphere, right?
Now, it depends on the vector. For example, if you are taking that vector, that can have both the values. And if you are taking the other vector, that can have both values. So that's where one bit, whatever you are telling today, can contain same values in the quantum physics. So it's not like the entire thing is like, wherever you're going, it's the same case. Like, basically, it is actually representing like X, Y, Z directions. But that one vector is having multiple values.
So, yeah, sure.
Yeah, we can take it offline. If there is no further, you have the business. Sorry. Yeah, thank you. Thank you, everyone.